right, thanks. Yeah, thanks for giving me a chance to talk this week as well, and thanks for your patience. I know some of you have heard me talk too much already. I want to tell you today a little bit about, I think it's very much work in progress, kind of advertise a little bit, I think, what was an interesting area of research for people in representation theory who think about categorification, and also people in low-dimensional topology who think about categorified invariants. So the main objects of interest in the talk are groups. The groups that I'll be interested in are auto-equivalence groups of triangulated categories. But if you're doing group theory, if you're a group theorist, a lot of times what you do is you try to find some interesting class of groups where you can you say things. I mean, they're very modern group theory very rarely says things about all groups. Usually says things about classes of groups. And there's some very interesting parallels between various classes of groups where analogous theorems and analogous objects are constructed. Mapping class groups of surfaces, automorphism groups of free groups, arithmetic groups. These various classes of groups are distinct, and there are independent theorems in all of these classes, but they kind of run in parallels, and there are dictionaries between the two. And my hope is that auto-equivalence groups of triangulated categories are kind of another class of groups that deserves to be put on the same page with mapping class groups of surfaces, maybe arithmetic groups, other groups like that. So I want to try to either convince you of that or at least tell you what some interesting questions are in this area. So to start, sort of the big motivating analogy here is sort of to think about triangulated categories kind of like surfaces. Well, I mean, a triangulated category is not a surface. A triangulated category for us is typically a linear object. A surface is not. So why is this perhaps a good thing to do? There are sort of two related reasons why this is maybe a nice analogy to think about. One is that some important examples of triangulated categories come from surfaces. Fukaya floor categories of surfaces are important examples of triangulated categories. So there, of course, you really do expect some very close relationships between the Fukaya category of surface and the surface. But another maybe more general thing, which is what I want to start telling you about, if perhaps some of you have seen it, but maybe hopefully not all of you, is an observation of Dikharov-Kapranov. So this board is about H. And Dikharov-Kapranov's observation, to summarize, is that triangulated categories are fundamentally two-dimensional objects, like surfaces. So what is this supposed to mean? Well, I'm not going to define a triangulated category for you, but I will tell you. But part of the structure of a triangulated category are what are called exact triangles. So an exact triangle is three objects of the category, and you've got morphisms, alpha from A to B, beta from B to C, and then gamma from C to a shift of A. So this is part of the structure you have in a triangulated category. So what Dikharov-Kapranov suggests is that we not use this notation for exact triangles, but rather draw them as triangles. Okay, so this is just notation, but this is the Dikharov-Kapranov notation for this exact triangle. So here, note, here the objects are labeling edges in this picture, and the morphisms are angles in the triangle. Okay? Now, why is that a good idea? Well, on the board here, here's a kind of classical picture in a triangulated category. This is, both of these are called convolutions. This is a picture where you've got two exact triangles, both of which involve the object C. And here you've got two exact triangles, both of which involve the object C prime, which is the cone of the map from B to E. So these are two pictures, and the octahedral axiom in a triangulated category says anytime you have a pair of exact triangles that fit together like this, then you get a pair of exact triangles that like this, and vice versa. So it's interesting to draw these two pictures in the Dikharov-Kapranov notation. So if you do it on this side, hopefully I did this right, you get this kind of picture. So I'm not drawing the morphism. So this is just, we've got two exact triangles, and they both involve this object C. And over here, if we draw this picture, we have this picture. So in Dikharov-Kapranov notation, the octahedral axiom in a triangulated category says anytime you have a convolution like this, you get one like this, and vice versa. Okay? And of course, you notice this is a flip between the two different triangulations of a quadrilateral. Sort of armed with this observation, there's a lot of things you can do. Dikharov-Kapranov used this to give models of Fukaya categories of surfaces by thinking about taking a surface of genus G, triangulating it, and labeling the edges of the triangulation with objects of your triangulated category, and then proving that they get something that's independent of the triangulation via this sort of things. I think maybe more vaguely, it's interesting from this point of view to think about various things one does with triangulations of polygons and surfaces in more general triangulated categories. What is a triangulation of a triangulated category? What should that mean? And various other sorts of things. So there's actually some meat in thinking about those questions. Huh?
So that looks like the 2-2 Pachman move?
That's right.
What's the correspondence of the 1-3 Pachman move?
That doesn't follow from abstract nonsense in a triangulated category. That's maybe something special. Yeah.
But for this independence that you mentioned, that should be important, right?
Yes.
Something is independent.
Yeah, that's right.
Then they use special properties of examples of triangulated categories, so is there a general?
Yeah, I think they study two periodic triangulated categories. They make some assumptions for some of their theorems. Yeah. But this is an interesting way to draw. I think this is, at a minimum, this is good notation in a triangulated category, and perhaps for this. And this gives you a nice way to think about various convolutions, possible triangulations of a disk, etc. Okay. So that's supposed to be a bit of motivation for what I want to talk about, which is an attempt to try to take some things that people do for mapping class groups of surfaces and try to do similar things for autoequivalence groups of triangulated categories. Okay. So for the next little while, I just want to forget about categories and tell you a little bit about some things people do in study when they in mapping class groups of surfaces. So apologies ahead of time to the topologists in the audience who already know this, but hopefully it will be useful. So I want to tell you a little bit about sort of Thurston. Of course, Thurston and others work on mapping class groups of surfaces. Okay, so here this is going to be sigma is going to be a surface, and the mapping class group of sigma is if you like, it's homeomorphisms, orientation preserving homeomorphisms of the surface. If the surface has boundary, it should fix these homeomorphisms should fix the boundary, and we just consider these up to homotopy. So the mapping class group, sigma acts on sigma. And okay, so how does so what are some basic structural theorems about mapping class groups that Thurston proves? Well, one, so in order to study a mapping class, we consider the action of the mapping class on isotopy classes of simple closed curves. Okay, and then a basic kind of, I'll make this more precise in a minute, but a basic dynamical question is if C is a curve and F is a mapping class, how does C grow when we apply F? When we consider, so we take this curve, we apply the mapping class group element to it, it's some other curve, and we apply higher and higher powers of this. And these are a bunch of curves on the surface, and we might want to measure how they grow as some sort of measure of how the mapping class group F is stretching us along the surface. So let's, so I drew a picture here that I want to spend a couple minutes looking at. So here my surface is a disk with 3 punctures, and here's a curve C. And the mapping class group element that I'm interested in here is sigma 2, sigma 1 inverse. So that's the mapping class that you get by doing a half-Dane twist around these 2 points, say counterclockwise, and then a half-Dane twist around these 2 points clockwise. So this is a famous example of Thurston that is drawn a lot in books. So I copied this from Farb Margolit's A Primer on Mapping Class Groups. Okay, so let's just look at what happens to this curve. So you see this curve, if we apply sigma 2, this is the curve we get. If we apply sigma 1 inverse, this is the curve we get. That's not too bad. Now if you apply sigma 2, you get this picture. Going from here to here is the first test of whether or not anyone is really kind of works with topology or surfaces. I mean, 2/3 of the audience, including me, will struggle to go from here to here. And then when you do sigma 1 inverse again, you get this. So how is this curve? So this curve is growing. One way you could look at one way you could measure how it's growing is you could ask, for instance, if I draw a vertical line here, you could ask in the isotopy class, how many strands are there going through that vertical line? And you could put a bunch of vertical lines in the picture and study how the strands are growing. So, so that measure of that growth rate is an important kind of dynamical measure for this mapping class. And so you might, for instance, want to have, say, some formulas for asymptotic behavior for how these number of strands grow. Now, at first glance, that's a very nonlinear thing, or it's not obviously a linear question. It's tricky to figure out how these Dane twists act, and therefore tricky to write down formulas or approximate formulas for how the number of strands grow. But Thurston had a fundamental and very beautiful idea, which is, to start with, he kind of introduced some shorthand notation for this curve. So this is a trivalent graph embedded in the surface. It's called a train track. And this is a labeled train track because I've just labeled the edges of this trivalent graph with numbers, which tell me the thickness, basically. This number labeled 10 here just means you've got 10 parallel strands going along here. So this is shorthand notation for this curve. It's a labeled train track, but it's just this curve. So in figuring out how a curve grows, you could act on train tracks and move them around and see how things grow. And that might not seem to be a much easier question than the original question, except sometimes this mapping class and this particular embedded trivalent graph will be compatible. What does compatible mean? Well, here's an example. So let's say you have this curve, which is given by a labeling of this trivalent graph. So that means I've got kind of x strands here, y strands here, and of course, you get this picture. But that picture is a different labeling of the very same train track you started with. So the mapping class and the train track are compatible in the sense that curves of this shape are preserved by this mapping class. Of course, the curves themselves are not preserved. The curves grow a lot, but their shape, as governed by this trivalent graph, stays the same. And there you see that the shape, so in other words, if you have a compatible train track in a mapping class, then to understand the mapping class, you could just look at how the thicknesses change in a compatible picture. And this is some linear map in the thicknesses. So this picture, for instance, if you have curves with thickness x and thickness y, and you apply this mapping class, then you get curves with thickness 2x plus y and x plus y. So the matrix that you write down is this matrix, which just tells you how the thicknesses transform. And now the growth asymptotics of this mapping class are just given by the growth of this Perron-Frobenius matrix. In particular, there's an important dynamical invariant of the mapping class, which is just the largest real eigenvalue of that matrix, and that invariant is called the dilatation of a braid. So let me give you a theorem, and then I'll write down that definition. So this is the Nielsen Thurston classification. Suppose beta is not reducible or periodic. I'll explain what that means in a second. Then beta is pseudo-Anosov. That is, there exists a pair of transverse foliations, measured foliations of the surface. So I'll write it down as it means. So beta of fu lambda. So maybe. Okay, so let me explain what this means. So where is the dilatation of beta? Okay, so we have a mapping class. Suppose it's not reducible. So reducible means it actually fixes an isotopy class of simple closed curves. If your braid fixes an isotopy class of simple closed curves, then you could imagine cutting your surface along that curve, and then you get two simpler surfaces, and you could study the braid by seeing what it does on those simpler surfaces. Those surfaces don't interact. So if beta is not reducible or periodic, meaning no power of beta is central, then what happens? Then the surface then beta stretches you in two directions on the surface. There's a pair of foliations of the surface called the stable and unstable foliation, and the mapping class stretches one of the foliations by lambda. Mapping class stretches you. The important point of this example is that this lambda, which is a stretch factor, it's a fundamental dynamical invariant of the braid, is computed by linear algebra via Thurston. It's the top non-negative eigenvalue of this matrix. So in particular, you have a nice corollary of Thurston's train tracks, which is that this stretch factor is an algebraic number. And it's the eigenvalue of it's an eigenvalue of a non-negative integer matrix, which is certainly not at all obvious from thinking of it as a stretch factor of a surface. That's right. So that's not obvious at all. That's part of the, and maybe Thurston was the first one to prove that, or I don't know who exactly did that, but that's right. So at a kind of nuts and bolts crucial aspect of all of this is why every pseudo-Nosov braid has a compatible train track. Compatible train tracks are not unique, but there is an algorithm to produce one due to Besswien-Handel that starts with a kind of arbitrary not compatible train track and improves it to a compatible one. So that's a crucial part of the story. Okay. All right. So and just for future reference, let me write down an example. So just as, because it'll come up again. So example, just of the numbers. So if the braid is, if we're in the four, so let's say we're in the 4-strand braid group, and this is our braid, then the dilatation is 2.29663. It's the root of, is the Perron-Frobenius root of this matrix. Okay. All right. So that's it for surfaces. Now we're going to move to categories. But the important, well, okay, one more comment about surfaces. So yeah, maybe one last comment. The last comment is if you really want to prove theorems about mapping class groups of surfaces and explore all these things, then the really important conceptual piece of mathematics you use is you use the action of the mapping class group on the Teichmuller space of the surface. So let me just write that fact down. So sort of organizing geometry. Which is incredibly important for establishing any theorem about these things, is the action of the mapping class group on the moduli space of hyperbolic metrics on the surface, Teichmuller space, and actually not just the mapping class group on Teichmuller space, but the mapping class group action on a compactification of Teichmuller space called the Thurston compactification. So Thurston defined a compactification of Teichmuller space. Why is this important? Well, because one of Thurston's theorems is that this compactification of Teichmuller space is just a Euclidean ball. So you get an action of the mapping class group on this Euclidean ball, and that's crucial for proving things about the mapping class group. For instance, you have a mapping class, it's acting on the ball, you think about that dynamical system. By the Brouwer fixed point theorem, it's got fixed points. You think about the fixed points. All of this stuff follows really from thinking about this. So you want to understand a mapping class, you want to understand how it grows. Thurston introduced some sort of linear algebraic techniques to study that question, and the important conceptual geometry behind the picture is this. All right. Okay, so any questions before we move on to categories? Yeah. I mean, actually, no, in the sense that you can give independent definitions of all the correct objects in the degenerate low genus, low punctures cases. But, yeah. Okay. So what I would love to do, and I certainly can't claim any really notable progress in this yet, but what I would love to do is take all of this and describe analogs for where instead of the mapping class group, you have the autoequivalence group of a triangulated category, and where kind of every object that one discusses in mapping class groups has some sort of analog, and describe that structure. So that's what I want to do. Okay, let me erase the board. So the rest of the talk is going to be tell you, at least in some special cases, parallels of all of this. Now, I should say, I think one thing that's interesting to do, and I think to some degree symplectic geometers and topologists probably already understand this, one direction that one could go, which is not the direction I'm going to go here, is take this specific example of a Fukaya floor category of a surface that has a mapping class group action on it, and try to reprove the various important theorems about mapping class groups via that action, the Nielsen Thurston classification, etc. So that's one direction one could go. Okay. So now let's. So now to triangulated categories. Okay. So now the next thing I want to try to do is show you an interesting example. So the example, we're going to be looking at the braid group of type A3. So this is the 4-strand braid group acting on the homotopy category of graded projective modules over the zigzag algebra, which those of you who went to talks last week heard a lot about. If you weren't here, it's okay. I mean, this is this triangulated category. You should think this has some spherical objects in it. And to each of these objects, there's a corresponding spherical twist. Which are autoequivalences of this category, and they generate an action of the braid group, the 4-strand braid group on this category. Okay. All right, so now I want to think about the braid this is the twist in P1, inverse the twist in P2, and the twist in P3. Okay, so I wrote a calculation on the next board, and I want to just show it to you. Okay, so on the left board, I've taken this braid, and I've just shown you what happens when you act on these basic generating objects with this braid. You get some new objects. These were actually modules over the zigzag algebra. You get complexes of modules when you act. Now, one thing to note about these objects is that they can be filtered so that the subquotients are just P1s, P2s, and P3s. So this guy just is 1 P2. This guy has a P1 sub, and then the remaining thing has a P2 sub. The remaining thing has a P1 sub. etc. This guy has a P1 sub, P2 sub, P3 sub. Okay? So you might want to measure, so you might try to think about the growth of this braid by thinking about these filtrations and saying, okay, suppose we act with higher and higher powers of the braid. Anytime you act, you get new filtrations just inherited from these, and you can just look at how the filtration multiplicities grow. So to measure this, you might try to measure the growth of filtration multiplicities So you could start backing in higher and higher powers of this braid and see how the filtration multiplicities grow. And you can see in this example, if you just use the filtrations inherited from this picture, then the growth of those filtration multiplicities are given by a matrix. 1, 2, 0. This is just saying, for instance, that this is like P1, this is P2, this is P3. This matrix just says when the braid acts on P1, you get a single P2. When the braid acts on P2, you get a P1, 2 P2s, and this is P3. Thank you. Okay. So you can compute the top eigenvalue of this matrix, and the lambda you get is much bigger than the dilatation of the braid. If there's a braid, it has a dynamical dilatation defined on the surface. Okay. So this gives you some bound on the growth rate, but it's not optimal. Of course, that's not the only way to filter objects. So I could instead now I have here's 4 objects, P1, P2, P2 to P1, and P3. And when I act here, the objects I get have filtrations by these objects. So I'll just draw them here. This guy's just one piece. So I've thrown in this extra guy. The importance of this computation is that anything which has a filtration by these 4 guys, if I apply the braid to it, the results will still have a filtration by these 4 guys. That's what this computation tells you. So you can compute how the multiplicities grow in this computation, and you get this matrix. So in other words, this is a different way to filter these objects, and you could look how these filtration multiplicities go. And lo and behold, in this example, if you compute the top eigenvalue of this matrix, it's exactly the dilatation of the braid. So this guy is equal to the geometrically defined dilatation of the braid. In other words, so the upshot of this is that one way to study growth rate of an autoequivalence is by finding some nice filtrations of the objects and studying the growth rate of those filtrations. What does nice filtration mean? Well, what happens here, so this was an example of a not very good filtration. What happens here is if you apply higher and higher powers of the braid, you get big complexes, and those complexes are not minimal complexes in the category. There's a lot of Gaussian elimination you can do in the complex. So applying higher and higher powers of the braid, what you get is very far from the nice minimal example of the objects. But here that's not the case. Here the point is, in this particular filtration is compatible with the braid in the sense that the filtration on high powers of the braid is inherited from these filtrations. So the upshot here is this braid is compatible with this nice set of objects, P2, P3, P2, P1, P2, what's the last guy I messed up? 1, P1. In that, what does compatible mean? The filtration multiplicities of the braid acting on, say, the nth power of the braid acting on the sum of these guys are just given by linear algebra. There's some matrix associated to the braid so this compatibility between this collection of objects and this braid is very much like Thurston's compatibility between a train track and a mapping class. Whereas for train tracks, the thickness of the strands was, in the compatible case, the thickness of the strands was changing according to a linear map. Here the filtration multiplicities are changing according to a linear map. So these guys are something you might call a train track. So let me state a conjecture. So these objects aren't just arbitrary objects, and these filtration multiplicities aren't exactly arbitrary multiplicities. So in the conjecture, I'll make this a bit more precise. For any braid, there exists a compatible train track that is a collection of objects now here I'll put in parentheses something that I'm not going to explain, but for those of you who were at the lectures last week, hopefully this will make some sense. So these objects are not just arbitrary objects. These objects are stable for a stability condition. So these objects are stable, which are stable for a stability condition on T. Such that the Harder-Nardin infiltrations of beta acting on the xi are given by some linear map applied to the Harder-Nardin infiltrations of the xi. So the canonical filtration of an object after you apply the braid is completely determined by the filtrations before you applied the braid. So this is a compatibility, and then when you had this compatibility, so when you had this compatibility, then you can make a definition. The largest eigenvalue of this matrix is what you might call the categorical dilatation of the braid. It measures the growth rate of the braid on the category. Now, it's certainly not obvious that this is well defined. I mean, even forgetting the fact that this conjecture asserts the existence of categorical train tracks. It's not obvious from the definition that such things, if they exist, should be unique, and they're certainly not. Just like for train tracks, they're not unique. The train track is not unique, but that top eigenvalue of the Thurston train track matrix is. And that's the case here too. So it's not, I mean, it's still conjectural that these things always exist, but when there exist many of them, this number is well defined. So that fact is a consequence of, so the fact that lambda is well defined is a consequence of the following theorem, which is that, well, this is not a great definition. I mean, we produce some matrix in some non-canonical way and say its top eigenvalue is something. So in the case of surfaces, the dilatation had a really intrinsically geometric meaning. It was a stretch factor in a foliation. It was telling you the direction which the foliation is stretching you. There should be a better definition of this, which is more analogous to that. I don't know what that definition is. So this is well defined, but this is the wrong definition. Of course, if it's the wrong definition, how are you supposed to prove anything about it? Well, fortunately, even if this thing doesn't quite have a good definition, its log does. So this is what's called the categorical, is equal to the categorical entropy of the autoequivalence. And this notion was introduced a few years ago by Hayden, let's see, four authors. Hayden, Dimitrov, Hayden, Kotsarkov, Kontsevich. So if you like, this whole thing is partially an advertisement of their work and their definition of entropy. What we're computing here with these stretch factors is the entropy the entropy they define is an infimum over an infinite set of things, but they prove that it's well defined. And the point of these, if you like, the point of these categories, it's very unclear how to compute the entropy of any autoequivalence according to the definition of these four guys. The way you should compute it, at least in these examples, is find a compatible categorical train track. And corollary, the DHKK entropy is an algebraic number. So corollary of the conjecture.
Question?
Yes?
This is invariant of what?
It's an invariant of the autoequivalence. Of the autoequivalence beta. So you have beta is an autoequivalence. It has an entropy which is defined however it's defined.
So it's not abstract proof, it's realized as autoequivalence on a particular case.
That's right, that's right.
So there might be different realizations for the same data and it will have different.
That is a fascinating question. Probably. In particular, what the dependence of this particular two representation of your group is completely unclear. And it's unclear because it's very difficult to do computation. Yeah?
But for example, if I run this machinery just for fun, the right category of resolution of Canyon singularity, will it find the same number?
Yes, but that's because that's the same. Yeah. But if you run it in homotopy category of Zergel bimodules, possibly you get something different. Yeah. Yeah. Right. So, yeah, so in the particular case, so now we'll say something rather specific. In the particular case that you have this, by the way, before I make this point, just to elaborate on Sergei's question. So on the Kleinian singularity example, there's an affine braid group action. So that affine one would agree with the affine type version of this. But if we're in finite type, so this is the ordinary braid group. So the conjecture, and this is almost a theorem of Ed and Keeseng, two of my PhD students, but they're still working out details. The conjecture is that in type A, categorical dilatation agrees with in type A in this particular representation. Categorical dilatation agrees with Thurston's dilatation. So first of all, this is the only case where you could make sense of that question, because for other types of braid groups, they're not mapping class groups of surfaces. But moreover, the sort of proof idea, or the reason why this is sort of approachable, is there's this, of course, this wonderful work of Kovanov-Seidel, which directly relates to this particular category to curves on the disk and the whole setup that one uses when one computes entropy. So this particular conjecture is largely an exercise in understanding the Kovanov-Seidel dictionary between two things. Yes?
Can I ask what categories the conjecture is supposed to apply to?
Okay, yes, that's good. So the conjecture should apply conjecturally to autoequivalences in any group G acting on a triangulated category generated by spherical twists. One might even also make a slight enlargement of this, or by Ricard complexes if you're doing actions of braid groups associated to Categorical groups. So in this generality, I think this should be true. I wouldn't have much intuition beyond that. Yeah. So. Yeah, that's a good. Okay, so. Yeah, so somehow of course, outside of, you mean in which compatible train tracks, that story, at least the Besvina-Handel algorithm, works for arbitrary mapping classes. It just degenerates to something, it just gives you something that where the kind of matrix you write down won't have, for instance, if the thing were periodic, then I think the eigenvalue you get is just 1. You get something kind of silly. But even if the mapping class is reducible, the algorithm still works. So, but you should, so I think one of the things which is interesting about this setup is that you should be able to produce new theorems analogous to theorems you have in mapping classes in the setting of triangulated categories which are not mapping classes. So for instance, the Nielsen Thurston classification, which says that a mapping class is either periodic or reducible or pseudo-Anosov, should have a cousin for these kind of groups. So this is kind of a question. how does one prove Nielsen Thurston like classifications for groups acting on triangulated categories, which are not mapping class groups. For example, if you're doing the braid group of type E8, then you have perfectly good categorical actions to use. The braid group of type E8 is not a mapping class group, so there's no existing Nielsen Thurston classification, but there should be one. And so, okay, well, I don't have a precise statement to make here, or at least not a very satisfying one. But what I do want to say is, how is one supposed to get at this? Well, in the case of mapping class groups, how does one get at the Nielsen Thurston classification? What you use is the action of the mapping class group on the Thurston compactification of Teichmüller space. This is a ball. The mapping class group acts on it. The Nielsen Thurston classification follows from a dynamical systems classification in this action. Different mapping classes give different kinds of dynamical systems acting on this ball. There's kind of dynamical systems classifications coming from looking at what the fixed points look like, and that's how you prove the Nielsen Thurston classification. So this is the kind of thing. If you really want to get at something like this, we need something like this. Now this Teichmüller space, this Thurston compactification is Teichmüller space, and then it's the boundary, projective measured foliations. This is like an open ball, and this is a sphere. And they glue up to give a closed ball. So this is the picture we need. Fortunately, so now let's say you have a group acting on our triangulated category. So one wants to produce from it something like this. And this part is already given to us. The role of the Teichmüller space in this story, at least for spherical twist groups, is played by the moduli space of Bridgeland stability conditions, which I talked about a little bit last week. So this guy is a very good analog of this. So the speculation is, if you really want to get at a classification like this, you probably need to compactify this space. And the question is what should go here? So so to tell you what should go here, let me tell you approximately how the Thurston compactification works. So the Thurston compactification, just in 2 minutes. So let's let capital S be the simple closed curves on the surface. So then there's an embedding of Teichmüller space into functions from simple closed curves to R. What is this map? Well, a point here is a metric. So if you have a curve, you can take it to its length in that metric. That gives you a map from Teichmüller space into this huge infinite dimensional vector space. There's also a map from the set of simple closed curves into this space by taking a curve x to the function that takes a curve y to just counts intersections between x and y. So that assigns to each simple closed curve a functional. So both these spaces, both these sets can be embedded into this space. And so, in fact, the Thurston compactification is the closure in projective space. I mean, these are non-negative So here, this projective space is like the projective space of rays, non-negative rays. You take the image of type Miller space in the projective space and you take the closure. And it turns out that this turns out to be type Miller space, disjoint union, the closure of this set in here. So in other words, the Thurston boundary is what you get by taking simple closed, the Thurston boundary is the closure of the set of simple closed curves in some sense. More precisely, it's projective measured foliations, but that's the idea. And you can do the exact same thing, in the last minute, you can do the exact same thing here. So in fact, if we let S be the set of spherical objects in T, then both of these guys, I mean, here actually I have to, both of these guys include into some common huge vector space. Like for instance here, I mean this is, instead of, so for a curve, it goes to the functional given by counting intersections. Here, an object goes to the functional given by taking the graded dimension of Hom. So taking Hom is, a natural thing to do for counting intersections. And so in this way, you can define a compactification in the same way. So this, in the same, just by looking at the closure of these spaces here. So, let me work this in. So conjecture, this is joint work with Anand Deyapurkar and Asalada Bapat. And type ADE, the compactification of stab we get here is a Euclidean ball that consists of stability conditions and a sphere. So if we prove that, then a Nielsen Thurston classification for braid groups of type ADE will follow. But, well, that's still conjectural. And I have absolutely no idea what happens outside of ADE. This compactification makes sense, this space makes sense in great generality, but I don't at the moment know how to prove anything about it, except in the kind of simplest non-trivial examples. Okay, I'll stop there.
Is there an interesting example where you can look at a sort of categorical action that should correspond to the Fukaya category of a higher dimensional symplectic manifold and see that something like this is true?
Yeah, I think I actually think the Dimitrov, Hayden, Katsartov, Kontsevich, their paper, I think their paper is called Dynamics and Categories. It's a wonderful paper, but they have a short section where they discuss examples of higher dimensional Fukaya categories. And they basically claim there that their categorical entropy agrees with topological entropy, which is maybe the only precise point you could make about that sort of thing. But I really think almost nothing is known. I mean, basically almost any question you ask, any reasonable question you ask is kind of uninvestigated.
I could think about, instead of thinking about the zigzag algebra, I could think about the category of homologies. Yeah.
Yeah, so that's I just started trying to think about that. I mean, that's the simplest example where you have two different categorical type A actions. They're related. The zigzag guy is a quotient of the Kavanagh guy. So exactly where, if anywhere, that the difference between them shows up in the categorical dynamics is completely unclear. I mean, the only few examples I've done, you get the same dilatation, for instance, in both actions. But you know, they're small examples. It's hard to do too many examples.
So in general, if I look at the eigenvalues of beta on the K group, the early group, does it use an
Yeah. So basically, if you look at the action on the K group, then the eigenvalue you get there will be an upper bound for the lower bound. Because, I mean, for example, you could think, one thing is, in these cases, there are pseudo-Anosovs which act trivially on the Grothendieck group. So their categorical dilatation and their topological dilatation will be greater than 1. But the bound you get, but in the K group, they act by the identity. So you get 1. Yeah, so you get bounds. You get slightly better grounds. You can also act on Hochschild homology instead of, look at the induced action on Hochschild homology, and there you also get bounds.
I could ask, is there a more intrinsic way to say when a tuple of objects is compatible than actually running this algorithm and counting multiplicities for?
Yeah, I mean,
Does the question make sense?
yeah, there's not a great way to say it, but there's also, I think, not a great way to say what it means for, for a train track, I mean, what you say is, the train track is, the point to keep in mind is a train track is some sort of shape for a curve, which is very different than the isotopy class of a curve. If you have an object in a category, which objects, whether or not an object has a filtration by these objects is a kind of shape of the object, which is very different from its isomorphism class in the category. And then, but in general, if an object has a filtration with these sort of objects and you act by an autoequivalence, you have no right to expect that the resulting object has a good filtration with these objects. So somehow the compatibility is about saying that the mapping class preserves things with filtrations like this. That's part of the compatibility. That's like preserving shape. Yes. Yeah, I mean, you can apply octahedral axioms and play all sorts of games which take filtrations of one kind to filtrations of some other kind, and those kind of flips and things like that seem to play the role of splitting in train tracks. That's a little vague. But.
If you take a spherical IBL category, then there is some special automorphism, autoequivalence that basically corresponds to Dollars and Thomas invariant. Is there anything reasonable to expect from entropy of this corresponding?
I have no idea. This is a good question. I have no idea.
Yeah, it looks like there's no further questions, so thanks again.